Hello, we are going to discuss about an interesting topic on negative refractive index. There will be a series of discussion on this topic. Today is the first one in this series and we are going to discuss about this. The moment we say refractive index, it immediately comes to our mind that we are talking about optics, or in common man's language, light, and how light passes in different mediums, what are the changes made in different mediums. We know that light itself is a part of electromagnetic spectrum. Light is a spectrum within the complete electromagnetic spectrum. So light behaves like an electromagnetic wave. Light waves are like electromagnetic waves. So light waves pass in any medium. Similarly, electromagnetic waves also pass in different mediums. So different mediums behave differently to different portions of the electromagnetic wave, whether it is in the optical region or non-optical region, radio region. So the medium, the propagation of the electromagnetic wave will depend on the medium. The medium itself is characterized by three fundamental characteristics. These characteristics are the conductivity of the medium, the electrical permeability of the medium, and the electrical permittivity of the medium. Since it is electromagnetic phenomenon, I am talking about electrical characteristics, not the optical characteristics. We will come to the optical characteristics later, which is the refractive index. This refractive index depends on these three fundamental characteristics. Out of these three fundamental characteristics, two fundamental characteristics, the permittivity of the medium and the permeability of the medium, they are responsible for the refractive index of the medium. Now these two, permittivity and permeability, being independent to each other, they are in a sense orthogonal to each other. Independence in terms of mathematics, mathematic people say that they are orthogonal to each other. Orthogonal means permittivity has no component on permeability, permeability has no component on permittivity. In other words, permittivity cannot be expressed as a function of permeability. Permeability also cannot be expressed as a function of permittivity. Therefore, if we consider a plane which is the permittivity permeability plane, then the plane will be described by two axes. One axis will be permittivity, the other axis will be the permeability. Based on these two axes or axes, we will characterize the medium depending on these two. The conductivity will not come into play right now. Later we will see the role of conductivity. So let us assume that we are considering a plane. If we are considering a plane for conductivity and sorry, for permeability and permittivity, we are also considering an electromagnetic wave which is propagating in that medium, which is to be characterized by these two quantities. The general form of the electromagnetic wave will be of the form E is equal to A exponential minus gamma. A is the amplitude of the electromagnetic wave. Gamma is the propagation constant of the electromagnetic wave. R is the distance from the source, how much distance it has traveled. Now, gamma or the propagation constant is equal to alpha plus I beta. I is the imaginary constant, which is root over of minus 1. Alpha is called the attenuation constant. Beta is called the phase constant. These are common for any person who is studying physics or who has interest in physics and who reads about electromagnetism or optics. Usually, both alpha and beta are positive. Now, if alpha is positive, then the exponential term will be exponential minus alpha into exponential minus I beta r. Now, exponential I beta r gives a propagating wave along r with phase constant beta. But exponential minus alpha r, alpha being positive, gives an exponentially decaying wave. So the amplitude A is decaying exponentially as per e to the power minus alpha r. With distance, it is decaying exponential. That is what this formula for electric field gives. Usually we require that alpha is equal to 0. Mostly we will deal with alpha is equal to 0. No attenuation is there. No loss is there. Attenuation means loss of energy. So it is not there. That is what we will assume as we proceed. Now we were considering a plane, permeability plane, to classify the medium in which electromagnetic wave is propagating. And this is the medium, the form of electromagnetic wave which is propagating in the medium. Now let us consider those parts, the plane part. Now in this plane, if we consider this plane, one of the medium can be dielectric, pure dielectric, which will be isotropic. Well, it may also be anisotropic. But mostly for simplicity, let us consider pure isotropic dielectric as one of the medium. So in this medium, there will be propagation of electromagnetic wave. Maybe there is some attenuation, but mostly it will propagate. If it is ideal dielectric, then there will be no loss. Alpha will be 0. Electromagnetic wave will propagate. Therefore, the electromagnetic wave, mode of electromagnetic wave in this type of medium is propagation mode. So we have a propagating mode or propagation mode. Other part is an evanescent mode. The evanescent mode means non-propagating mode. These are examples of non-propagating mode is plasma or metal. So these are types of mediums. Plasma is a type of medium. Metals at terahertz half frequency. These are types of medium where electromagnetic wave stops propagating or gets attenuated over certain frequency, in certain frequency range, There is a cutoff frequency range. Below that or above that, depending on which medium we are considering, it will start to attenuate. Usually, in these mediums, the permittivity is negative. Negative permittivity gives such type of medium, evanescent mode or evanescent medium. Why? That we'll see later. But for the time being, remember that if permittivity is negative, then we'll have an evanescent mode, which is a non-propagating medium where there will attenuation. Similarly, if permeability is negative, like ferrites, those type of mediums also give rise to evanescent modes and there will be attenuation. So those mediums are attenuating mediums. The mode of propagation is evanescent mode. Now these three we know. So now let us look at the plane. Epsilon r is in the x-axis, or permittivity is in the x-axis, permeability is in the y-axis. So the first one, both epsilon r and mu r, both are positive in the first quadrant. In the second quadrant, mu r is positive but epsilon r is negative. Third quadrant, we don't know what happens, where mu r and epsilon both are negative. Fourth quadrant, epsilon r is positive but mu r is negative. So first is propagating, second and fourth are evanescent. So this we know, already we know. Now looking at this, Russian physicist Veselakov, he thought, what will happen if we are in the third quadrant? In the third quadrant, both mu r is negative, epsilon r is negative. If both these are negative, what is going to happen? If we have such a medium where mu r is negative and epsilon r is negative, what is going to happen? Whether there will be propagation or there will be non-propagation or attenuation. Now look at what is beta, the phase constant. This is defined as 2 pi by lambda. Now lambda is v by f, phase velocity by f, frequency. So if you put that, then beta is equal to 2 pi f by v, or 2 pi f is omega, so omega by v. Now v, velocity, is speed of light divided by root over of mu r into epsilon r. So put that for v is equal to, for v put c divided by root over of mu r into epsilon r. So accordingly beta will be 2 pi f or omega into root over of epsilon r mu r by c. Now if both epsilon r and mu r both are positive, beta will be positive. If one of them is negative, then this root over sign will be imaginary, so beta will be I beta, then gamma is equal to alpha plus I into I beta, that is minus beta, so that will be again attenuation if any one of them is negative. Now if both of them are negative, we have to find out what is going to happen to this root over. This root over will give us, if we find out what is going to happen to this root over, if this root over is positive, then there will be propagation mode. If it is negative, then there will be attenuation. So let us see what is going to happen if beta is equal to 2 pi f root over of epsilon r mu r by c, when both are positive, both are negative. Next question is, once we say that, the next question is there any condition in physics according to which both permittivity and permeability can be negative? Is it possible as per physics? So look at the laws of physics, whether this is possible as per laws of physics. Now either the laws of physics are preventing them or approving them. Both of them being negative, is either prevented by laws of physics or approved by laws of physics. Now look at the prevention. Does it prevent? There is not a single law which prevents the existence of negative permittivity and permeability simultaneously. So no known law of physics prevents their existence. Does it approve it? It approves it conditionally. Under certain conditions only, both of them can be negative according to laws of physics. Now, what can be those conditions? The condition is it must satisfy the generalized entropy condition for a dispersive media. Dispersive media means the characteristics of the media is changing with frequency. For example, beta is equal to beta of f square, which means beta is a function of f square, f being the frequency. If this condition is satisfied, then both mu and epsilon can be negative. Now, once we know that both can be negative, accordingly Vasilego made some conclusions. Let us look at those conclusions one by one. First conclusion he may derive is, and the propagation constant beta will be negative. Beta we have seen 2 pi f by c into root over of mu r epsilon r. If both mu r and epsilon are negative, then this root over will be negative and beta will be real. So propagation constant beta is real and negative. That is what he concluded. Next. Since beta is real, therefore there will be propagating mode. So propagating mode will exist. So in the third quadrant, if the material is classified into the third quadrant, it will have propagation mode. No evanescent mode. Next. Now, there will be propagation, but under this condition, the group velocity and phase velocity will be antiparallel, which means if group velocity is in the x direction, phase velocity will be in the minus x direction. So they will be antiparallel to each other. Next. Because of this antiparallel nature of the two velocities, the propagation will be called backward propagation because phase velocity will be in the antiparallel direction. So we will call it a backward propagation. That is what he concluded and he gave this name backward propagation. Next. In this backward propagation, the phase velocity will be minus omega square root over of LH CLH. LH is left hand. So LHCLH, this is considering the circuit equivalent of a material with mu negative, epsilon negative. Similarly, Vg will be omega square root over of LHCLH. So now you can see Vp and Vg both have same magnitude but opposite directions. Now, since they have same magnitude and opposite directions, now if you multiply them, Bp into Vc, usually that is from physics we know that is Vp into Vg is c square. Here it is minus omega 4 LLH CLH, that is not equal to c square. That does not equal to, it is not equal to c square. So this is a condition in which the product of Vp into Vc, phase velocity into group velocity, is different from c square. It is not c square. Then the third conclusion, important conclusion was because both are negative and beta is negative, and therefore the refractive index is also negative. Why beta becomes negative? Because it is 2 pi f by c. All of these are positive into root over of mu epsilon. Root over of mu epsilon is negative, but root over of mu epsilon is the index of refraction. N is equal to root over of mu epsilon. Now, since root over of mu epsilon is negative, therefore, index of refraction is negative. That is what Vasilego concluded. So N, as you know, N is equal to C over Vp, Vp being the phase velocity. Now phase velocity is negative, therefore refraction index or index of refraction is negative. So on, so this is established. N is negative, that is established in this manner. Next. So accordingly, we can classify the media as double negative media or any other media. So mediums we can classify according to electromagnetic characteristics. Let us consider an isotropic homogeneous medium. In an isotropic homogeneous medium, D is equal to epsilon 0 epsilon E, B is equal to mu 0 mu H. Now, if in this, if epsilon is greater than 0, mu is greater than 0, both are positive, then this medium is called a double positive system. This type of medium is double positive medium. Next. And in DPS medium, propagation will occur. Both are positive, propagation will occur. Now suppose epsilon is negative but mu is positive, then this is called electrically negative medium. ENG is electric negative medium. In this there will be no propagation, there will be attenuation. Next. If epsilon is positive but mu is negative, this is called magnetically negative medium. So in this medium also there will be no propagation. Both these come under the category of single negative medium. In this single negative medium, there will be no propagation, there will be attenuation. So these are supporting evanescent modes. So these mediums are evanescence medium. Finally, if next, epsilon is negative, mu is negative, both are negative, so this is called double negative medium. In the double negative medium, propagation will occur, so there will be propagation. So today we have classified electromagnetic medium into 4 categories. Next time we will see from this point onward, from this classification onward, we will see in the next discussion. Thank you.